Okay, so in this video, we are going to develop a numerical measure that can quantify the direction of the relationship. So we will consider the direction of the relationship. And then what is the direction? How can you quantify that? And the idea of the direction is when we say the relationship is positive, like upward sloping or downward sloping, we can say that like when, so by the way, the, the horizontal axis says it is always x variable. The variable on the horizontal axis is x and vertical axis has y. So when the relationship is positive, that means when x increases, y tends to increase, then positive. Or equivalently, when x decreases, y tends to decrease, then the relationship is positive. Otherwise, if like, so we may change the direction. Like if the relationship is negative, then when x increases, then y decreases, or when x decreases, then y increases. So that's the basic underlying idea behind the direction when we say about the direction. And then we are going to quantify that. First, when we say decrease or increase, the reference point, the starting point, will be chosen by the mean. Will chosen as the mean. We are going to start from the mean. So suppose that this point is the center, x bar and y bar. So the sample average of x and y will give the center of the two-dimensional scatter plot and make quadrants, 4 quadrants. So divide the plane into 4 quadrants, and then we can divide the observations by the observations, so that the first quadrant on the top right, like say top right side, top right panel, has the observations such that x is greater than x bar and y is also greater than y bar on this area. So that means you can say that x increased and also y increased from their respective averages. And so this area, the first quadrant, includes observations that imply positive relationship. And same idea applies to the third quadrant. Here on the bottom left side is that x is smaller than x bar and y is smaller than y bar. So when x decreased, y also decreased. So therefore, they move together. So the relationship is positive here. So this and this area have implied positive. The observations on these two areas imply positive relationship. And the other side, the second and the fourth quadrants, have different direction for x and y. So x increases but y decreased, and here x decreased but y increased. So in that sense, these two quadrants have observations that imply negative relationship. And then the problem is, say, that as you can see, some observations imply positive relationship and others imply negative relationship. So if all the observations are only on one like the first one side, then it'll be easy to tell, but it's not. Almost always you will see some observations almost in every quadrant. Therefore, to quantify, we are going to calculate some kind of average of their relationship. So the idea is like this. We will multiply their changes from their average. So change in x and change in y. If both moved together, if both increased or both decreased, then this will be positive, or negative. So their multiplication will be always positive. You get it? When x and y move together, their changes will have the same sign. Therefore, when you multiply them, the product is always positive. And however, if they move in the different directions, then when change in x and change in y will have different signs. One is positive and the other will be negative. So their multiplication will give you a negative number. So our idea is to calculate this for each observation, right? So for each point, you can calculate their changes from the center, right? Deviation, so deviation in x, deviation in y can be calculated for each observation. So for each observation, multiply them. That will be there will be as many product of deviations as the number of observations. Therefore, we are going to average them. And if the average is positive, we will say positive relationship is dominant, so the overall relationship is positive. If their average is negative, then the overall relationship is more toward negative. So we say negative. This is the idea of how we quantify the direction of the relationship. So numerically, it's like this. The covariance is what I just said. Covariance is the average of the cross product of deviations. As I said, there are two variables. Calculate deviations for each observation for each variable, and then multiply the two deviations for x and y. And some may have positive products and others may have negative products. So average them out. If the average is positive, then the overall relationship is positive, otherwise negative. Numerically, the formula goes like this. Covariance between x and y, random variables, x and y, will be calculated like this. Deviation in x, deviation in y, multiply them, and sum and divide by n. But the reason why we use n-1 in the denominator is because only when we use this is unbiased only when we use n-1 in the denominator. We learned a similar formula for the variance. For variance, there was the sample formula or the population variance formula, and in the same way, the covariance can be calculated using denominator n or n-1, and we just call them different formulas. But usually, sample covariance formula is more commonly used. And another thing you can find here is if x equals to y, so think about y was actually the same variable as x. So replace this y with x. Then they are the same deviation, so x bar squared, it will become x deviation squared. So then the covariance comes down to a variance, right? So you can understand it as the variance is a special case of the covariance, or the variance is a covariance between x and x itself. So you can think about relationship between the same thing. What is the relationship with me and myself, right? So that is the variance, right? So covariance is a more general, mathematically more general measure. And so far I just explained the intuition, but let's think about a simple numerical example with only 3 countries. So usually you can extend it to any number of observations, but for simple practice, for exercise, we are going to consider three countries: Canada, US, and Mexico. And the temperature, I just chose simple numbers. They are not, I tried to make them more realistic, but not exactly real numbers. So suppose that the temperature, average temperature in Canada is -5 degrees, and US 10 degrees, Mexico 25 degrees, obviously warmer as you go down. And the GDP per capita in Canada is 35,000, US 40,000, Mexico 15,000. We would like to calculate the covariance to understand the direction of their linear relationship. But just from, even though you have only three numbers, still it is not clear. So temperature increases in this direction. Temperature increases, but GDP per capita increased and then drops a lot. Increased and dropped. So the order is not clear. If the order was perfect, then it would be easy to see what is the direction, what's the relationship. But because it's not clearly decreasing or increasing, you need to calculate the covariance to determine whether it is positive or negative. The idea is simple. How to calculate the covariance? First, calculate the mean. It's like similar to calculating the variance. You first need to choose the center, the mean, and then mean is like the temperature is mean temperature is 10, and mean GDP per capita is $30,000 among these three countries. And then, like what we did in the variance calculation, we calculate the deviations. So, for example, the average temperature is 10. So Canada is 15 degrees below the average, and Mexico is 15 degrees above the average, and US is exactly the average, right? So this captures the deviation of temperature, average temperature. And Y, do the same thing for Y. So the average GDP per capita is $30,000, and Canada is $5,000 higher than the average, and US has $10,000 above the average, but Mexico has $15,000 below the average. So deviations for each variable is calculated for each observation. 3 observations, 2 variables. So there are 6 deviations. And then multiply them. So for Canada, multiply the deviation of temperature to the deviation of GDP per capita. For US, for Mexico, and if you multiply, you will get these numbers. So there are 3 numbers, and as I said earlier, what they imply is that Canada has negative number, which implies negative relationship. Also, Mexico has a negative number, which also implies a negative number. And US has 0. It's in the so 0 times 10,000 is 0. So clearly it's overall negative. And to be more rigorous, we are calculating its average. But when you calculate the average, one tricky point is that the denominator may be n-1, not the sample size. So even though we have 3 observations, denominator is only 2. That's actually very annoying. It's very, very annoying. So annoying. But that's the rule, so I cannot change that. Okay? And graphically, this is what you see if you have a scatter plot. Make a scatter plot, 3 points, then the trend line will be like this. This line, it fits those 3 points best. So colder countries, and it looks like colder countries, Canada or US, tend to have higher GDP per capita than warmer countries. Okay, that's what we can tell from the covariance. So then I will give you an exercise opportunity. So now let's change the data. Idea is the same, but now let's change the temperature into Fahrenheit. Fahrenheit, then if you switch the numbers to Fahrenheit, you're going to get these numbers. And GDP per capita can be abbreviated in $1,000, can be shortened by deleting 3 zeros. So GDP per capita is now measured in $1,000, and we are going to relabel those random variables as W and Z. So we change it their units, and I kindly calculated their averages for you. So in Fahrenheit, the average temperature is 50, and in $1,000, the average GDP per capita is 30. So so now the new data look like this, and using this data, try to calculate the covariance. Of course, use the sample covariance formula and calculate to the algebra. And then when you finish the work, then come to the next video. I will show you how to work on this. See you later. Bye.